Let's talk about JOS Memory Layout. So this is the address space of a user program. What we see here is we have unused memory at the bottom, with possibly the symbol table at the user S tab. Now, note here this page table size, so the PT size. The PT size is the amount of memory that one page table can address. So if you think that a page table is a page big, so that's 4096 bytes, each entry is 4 bytes, so that means there are 1,000 entries in a page table. And each page table is responsible for 4K of memory. So the page table size is 4 megabytes. So basically what we've got is 4 megabytes down at the bottom, which may include the symbol table. Another 4 megabytes used for temporary memory that we'll see later. So that's just something that the process has available for later mapping. Above that, at uText here, is where the process is loaded. So that's where the text segment, the data segment are located. The heap goes above that. What we see at the top here, right at the top, is the stacks. So if we look at the stacks, there are actually 2 stacks. So there are the normal user stack here, and then there's also an exception stack. JOS is not like x86, it's not like a traditional Unix kernel. Instead, it's what's called an exo kernel. So there are lots of facilities that normally are hidden in the kernel that are actually provided to user programs. So among them, the user process can actually handle faults, so page faults and other sorts of faults. And when a page fault occurs, rather than running on the user's stack, the normal stack, it actually runs on a separate stack, still in user space, but dedicated for handling exceptions. So that way, this exception handling code cannot interfere with the regular code that's running. That's everything the user process can read and write. Above here, we have the portion of the address space that is reserved for the kernel. So the first thing we have are the environments. So the environments are what we would call in a traditional operating system the processes. So, but in JOS, they're called environments. So this is basically the table of such environments. Above that, we have the pages, and the pages are these page info structures. So they're information about the physical pages. So for every page, is it in use? How many references are there to it? And a linked list sort of these. Above the pages then, we have the current page table. So this is basically all of the page table entries linearly set out. We'll look and see how that's done in a different video. Above that, we have the memory mapped I/O. So this memory mapped I/O in physical space is at the top of the address space. We happen to be mapping it here in the address space. And then above that, we have the stacks. So we actually have multiple stacks. And the reason for that is this operating system can support multiple CPUs running in the kernel at a time. So each of them has its own separate stack. So it has its own stack and then also its own stack guard, which is invalid address space to ensure that we're not writing outside of the stack. Here we get kernbase, and kernbase is 256 megabytes from the top of the address space. So it's the top 1/8 of the address space. And this is where all the physical pages are mapped. So this is why JOS is limited to using a 256 megabyte hardware. So it only uses that 256 megabytes because that's the only address space it has to map in all the physical memory. So that is how JOS's virtual memory is laid out. Like in x86, there's an easy way that the kernel can get access to physical pages. So if it wants to get access to any particular physical address, it can just add this kernbase to it and there they'd get a virtual address that refers to that physical address.